While one class got through example 2.2.5 on Thursday, one class did not. So I'm making a video to remind you of the different types of conditional statements. So we've already seen a conditional statement if P then Q. So we have other types of conditionals that can also exist. One such is the contrapositive. Contrapositive says, if not Q, then not P. And the interesting thing about the contrapositive is it is logically equivalent to the conditional statement, as we're going to see from the two examples below. We also have a converse, which says if P then Q. And we're going to find out that this, in terms of when we get into proof writing, is basically putting the cart before the horse. This is assuming what is to be proven before we've established what it is that we're supposed to assume. We're saying if conclusion, then hypothesis. So obviously that's not going to be logically equivalent to if hypothesis, then conclusion. So we call that a converse fallacy. Another fallacy we have is the inverse. The inverse fallacy says if not P, then not Q. So if not the hypothesis, then not the conclusion. Well, that's also not necessarily the case. So we'll find that the converse and the inverse are logically equivalent to one another, but they are not logically equivalent to our contrapositive and our conditional statement. But our contrapositive and conditional statements are logically equivalent. If this sounds a little confusing, I have a table just below this example that will show you that reminder. Or maybe it's just a bulleted list, but I think it's a numbered list. So I'll have it organized below just in a moment, but let's see what some of this looks like in practice. So if Howard can swim across the lake, then Howard can swim to the island. So if P, then Q. Our P is Howard can swim across the lake. Our Q is Howard can swim to the island. So our contrapositive says, okay, negate both and switch the order. So my contrapositive would say, if Howard cannot swim to the island, then Howard cannot swim across the lake. And that makes sense, right? Because the island is, assumedly in the middle of the lake, or perhaps closer to one shore or the other. But if Howard can't swim to the island, then Howard certainly cannot swim across the lake. So it makes sense that this is logically equivalent to our conditional statement, that if Howard can swim across the lake, then he can swim to the island. What is not logically equivalent to this is our converse. Our converse says switch the order. And that's it, just switch the order. If Howard can swim to the island, then Howard can swim across the lake. Well, not necessarily true, right? Again, we're assuming the island is closer to the shore than the other side of the lake is. So then Howard can swim across the lake. Our inverse says, okay, fine, then just negate the P and the Q and leave them in the same order. If Howard cannot swim across the lake, there we go, the lake, then Howard cannot swim to the island. Well, what if the island's really close to this shore? Maybe Howard can just walk to the island. Maybe he doesn't even need to swim. Wow, my across looks terrible. Let me rewrite that. Across, there we go. If Howard cannot swim across the lake, then Howard cannot swim to the island. So we can see that the two statements in blue are equivalent to one another, but they're not saying the same thing as our contrapositive or our given conditional. Let's try another example. This one's a little easier to put into place, especially because it's already Labor Day weekend. So for this one, I said if today is Labor Day, then tomorrow is Tuesday. Well, today is Labor Day is our P, then tomorrow is Tuesday, makes tomorrow is Tuesday our Q, if P then Q. What does our contrapositive say? Our contrapositive says if tomorrow is not Tuesday, then today is not Labor Day. And that makes sense because Labor Day always falls on a Monday. So you can't have Labor Day on a non-Monday. So that makes sense. And we can see that those two statements are logically equivalent. But what happens if we start looking at our converse and our inverse? Our converse says, okay, just switch the P and Q. If tomorrow is Tuesday, then today is Labor Day. That doesn't make sense because there are 51 other Mondays that aren't Labor Day. We don't have only one Tuesday in the year, so this doesn't work. We can see that this is not logically equivalent to our conditional or our contrapositive. We're going to find the same thing with our inverse, which is going to essentially say the same thing as our converse. Our inverse says if not P, so if today is not Labor Day, then not Q. Then tomorrow is not Tuesday. Once again, there are 51 other Mondays that today could be. Even if it's not Labor Day, we still have 51 other Mondays. That would be essentially saying we only have one Tuesday all year. So as we can see, that also wouldn't be logically equivalent to our conditional or our contrapositive. So I've left you with an ordered list here of those logical equivalencies. So a conditional statement and its converse are not logically equivalent. A conditional statement and its inverse are not logically equivalent. However, the converse and inverse of a conditional statement are logically equivalent to one another. And we also know the conditional statement and its contrapositive are logically equivalent to one another. I also left you a list of definitions to use. I think I put one of these on the homework. And those are different terms you might see listed in your book or in other proofwriting examples. So you might see only if. P only if Q means if P then Q. Or if not P then, or sorry, if not Q then not P, aka it's a conditional statement or it's contrapositive. Biconditional is something we're going to be seeing a lot more of, and we also call these if and only if statements. That says P if and only if Q, and it's given with this cool dual-headed arrow. It is true if both P and Q have the same truth values and false if they have the opposite truth values. We'll see, especially when we get into chapter 4, that we will abbreviate this with IFF, if and only if. I also gave you definitions for sufficient and necessary. And then I gave you some other ideas. If R is a necessary and sufficient condition for S, it means R if and only if S. So there are just a few definitional things there that you might want to look through, and you should be able to find, I think there's one problem in the homework from this section on, I believe it was a necessary condition, maybe a sufficient. So the definitions are there, and you can use those to apply them to the Cengage online homework.